Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Lesson 23, Comparing Rational Expressions. Rational, for starters, hopefully you all know what the number system is. Naturals, rational, irrational, whole, integer. You need to know what all those mean. The root word for rational is ratio, and ratio is just expressing or comparing two things, and it usually really just means a fraction. Okay. So classwork opening exercise says, use the slips of paper you have been given to create visual arguments for whether 1/3 or 3/8 is larger. Well, obviously I can't pass paper out to you through the internet. So in my video, I brought this diagram in, and this is 1 out of 3. And it's 2 sheets of paper that are the same size. And this is broken up into 8 pieces. 1, 2, 3, 4, 5 are white and 3 are blue or shaded. So that's 3/8. So as you can see, this carries over just a little bit further, but hopefully let's see, there's an easier way or a better way to. Their visual representations are always good, but you need to also realize that a fraction in your calculator is just simply division. So if I take 1/3, that just means 1 divided into 3 pieces. 1/3 is 0.3 repeating, and 3/8 is 3 divided by 8. And if I put that in the calculator, it's 0.375. Well, obviously 0.37 is more than 0.33. So an easy way to determine if a fraction is larger than another is throwing it in your calculator and seeing what it is as a decimal. And you don't need a calculator to do that either. You can always do long division. So carrying on to the exercise now, it says, we will start by working with positive integers. There's another word, integer. What's an integer? Well, it's a number that's not a decimal or a fraction. Negative infinity to positive infinity. So -3 is an integer, -2, -1, 0, 1, 2, 3. They're all integers, but there's no fractions or decimals in the integer group. So let m and n be positive integers. So here's n given to us, 6 numbers, 1, 2, 3, 4, 5, 6, no fractions, no decimals. Work through the following exercises with a partner. So it says, fill out the following table. Here's n. What would 1 over n be? So 1 over n is obviously 1 over 1 because n is 1. So these are all going to be 1 over what's in the column to my left. So I'm just going to do this now, 1 over something. So this is 1 over 2 or 1/2, and this is 1 over 3 or 1/3, and this is 1 over 4 or 1/4 or 1/4, and this is 1/5 or 1 over 5, and this is 1 over 6. Okay, so there it is. There's the following table. Now it's number 2 says, do you expect 1 over n to be larger or smaller than 1 over n plus 1? Well, 1 over n is equal to 1, so this here is equal to 1. This is equal to 0.5, and this is equal to 0.3 repeating. Okay, and this is equal to 0.25, and this is equal to 0.2. And 1/6 is 6 goes into 10 once with a remainder of 4. 6 times 6 is 36 with a remainder of 4. So it's 1.6 with the 6 repeating. So what are these numbers doing? 1/2, 1/3, 1/4. And as decimals, 0.5, 0.3, 0.2, 0.1. Well, what are they doing? They're getting smaller. So I brought this in to show you a visual. Here is a 1/2. Here is a 1/3. Here's a 1/4. Here's a 1/5. Here's a 1/6. So if you think of a piece of pizza or pie, if you cut it into smaller pieces and you only get one of those pieces, are you getting more or less of that pie? Okay, so do you expect 1 over n to be larger or smaller than 1 over n plus 2? Well, look up here. So here's 1 over n, and I got 0.5. 1 over n, which is 2, plus 2 is 1 over 4. So adding 2 just brings us down 2 here. So there it is a 1/2 1 over n more than or less than 1 over n plus 2, or 1/4 or 0.25. Well, 1 over n is larger than 1 over n plus 2. And there's basically my explanation why, but I'll give you an explanation. Okay, so from the table, as n increases, 1 over n decreases. This means that since 1 plus n is greater than n, we will have 1 over 1 plus n will be less than 1 over n. That is, 1 over n is greater than 1 over n plus 1, which is greater than 1 over n plus 2. So the bigger the denominator gets, the smaller the fraction becomes, or the number, the decimal. Okay, page 2 brings us to number 3. Compare the ratios, compare the rational expressions 1 over n plus 1, and 1 over n plus 2 for n equals 1, 2, and 3. Do your results support your conjecture for exercise 2? Revise your conjecture if necessary. So let's go back to our conjecture, because I know I made a mistake where I circled something. 1 over n is going to be, no, that's right. It's going to be larger, because I think I just changed it. It was smaller. 1 over n is larger than 1 over n plus 1. 1 over n, let's say n is 2. N plus 1 would be 3. 1/2 is greater than 1/3, and so on. So 1 over n is definitely going to be larger than 1 over n plus 2. So there's our conjecture. As the denominator gets bigger, the number gets smaller. That's our conjecture. So here we have the scenario where n equals 1, 2, and 3. So for n equals 1, we're going to do here. N equals 2 will go here. And I'll put n equals 3 in this row here. I'll do the 1 over n in red. Okay, so let me just move this down a little bit. And then this is going to be 1 over n. So when n equals 1, I get 1 over 1. If n equals 2, I get 1 over 2. If n equals 3, I get 1 over 3. This is obviously 1. 1/2 is 0.5, and 1 over 3 is 0.3 repeating. So then if I do 1 over n plus 1, well, that's going to be 1 over 1 plus 1, which equals 1 over 2. This is going to be 1 over n plus 1, which equals 1 over 3. And this is going to be 1 over n plus 2. So that's going to equal 1/5. Okay, so we have this equal to 1, and this is 1/2, and this is 1/3. Now we have 1/2, 1/3, 1/5. Now let's do 1 over 3. So if n equals n over 3, 1 over n plus 2, and my n is 1, that's going to be 1 over 1 plus 2, which is 1/3. This is going to be 1 over 2 plus 2, which is 1/4. And this one will be 1 over n plus 2, which equals 1 over 5. And I made a mistake here. This is supposed to be a 1. So therefore, this is supposed to be a 4. Okay, so now if I erase these and get them out of the way, and erase these and get them out of the way, does our conjecture hold true? Well, 1 is greater than 1/2. 1/2 is greater than 1/3, and 1/3 is greater than 1/4. 1/2 is greater than 1/3. 1/3 is greater than 1/4, and 1/4 is greater than 1/5. So it says, do the results support your conjecture? And the answer is yes. As the denominator increases, the actual entire ratio value decreases. So number 4 says, from your work in exercises 1 and 2, generalize how 1 over n compares to 1 over n plus m, where m and n are positive integers. Okay, so what we would say is, since m is a positive integer being added to n, the denominator will increase, which will decrease the value of the rational expression overall. That is, 1 over n will always be greater than 1 over n plus m for all positive integers m and n. Number 5 says, will your conjecture change or stay the same if the numerator is 2 instead of 1? Well, it says to make a conjecture. So let's just do some examples. So now we're going to change the numerator to 2. Well, let's do 2 over 1. That equals 2. Let's do 2 over 2. That equals 1. Let's do 2 over 3. That equals 2/3. Or let's put it into decimal so we can compare. 2/3 is 0.67 rounded. How about 2 over 4? Well, that's a half, 0.5. And 2 over 5 is 1 over 10. Or 2 over 5 is 4 over 10, or 0.4. So what's happening? 2, 1, 3/4, 0.2, or 0.5, 1/2, 2/5. It's getting smaller. So it says, will your conjecture change or stay the same? Well, it will stay the same. Even though the numerator is bigger, if the denominator gets bigger, the whole thing will get smaller. So I'll put that into words for you. Okay, so in words, we would say it will stay the same because this would be the same as multiplying the inequality by 2, and multiplication by a positive number does not change the direction of the inequality. Oh, that's a great way to put it. If the numerator is held constant and the denominator increases, you are dividing by a larger number, so you get a smaller number overall. So there you have it. Okay, page 3 brings us to an example. So let's do it. So this is a table with x values, and this is a function x plus 1 over x, and this one is x plus 2 over x plus 1, and we're just going to substitute in. So I'm going to just do this. There's not a whole lot of room to show work, and I think we're beyond having to show this kind of work at this level, so let's just go. So this is 1/2 plus 1, which is 3/2 over 1/2. And if you're still not being able to picture that, that's 3/2 divided by 1/2. And that's the same as 3/2 times the reciprocal of what you're dividing by, which is 2 over 1, and that cancels and gives us 3. Okay, so then 1 plus 1 is 2 over 1. 2 over 1 is simply 2. So maybe there does require some scratch work off to the side here. 1.5 plus 1 is 2.5. 2 and 1/2 is 2 and 1/2 is 5/2. And if we divide that by 1.5, which is 3/2, that's, or divide it by 3/2, it's the same as multiplying by 2/3. So we're going to get 5/3, which is 1 and 2/3, which is 1.66. Repeating. Plugging in 2, we get 2 plus 1 is 3 over 2. 3/2. I'll just put it as 3/2. That's 1.5. Now let's do decimals. Let's do decimals. 1.5. It's easier to see if something's larger or smaller looking at a decimal. 1.6 is definitely greater than 1.5, obviously. Okay. 5 plus 1 is 6. 6 over 5. 6/5. 6/5 is 1 and 1/5. And 1/5 is 2/10 or 0.2. 1.2. 10 plus 1 is 11 over 10, which is 1 and 1/10, which is 1.1. And 100 plus 1 is 101 over 100, which is 1 and 1/100th, which is 1.01. Okay, so there's that first column. Now let me get all my messy work out of the way here. Alrighty, and let's switch to purple this time. So we have 1/2 plus 2 over 1/2 plus 1 equals, well, this is going to be 2 and 1/2, which is 5/2, divided by 1 and 1/2, which is 3/2. So it's 5/2 times 2/3. These cancel, and we get 5/3, which is 1 and 2/3, which is 1.66, repeating. Okay, and then this one is 1 plus 2, which is 3, and 1 plus 1, which is 2. That's 3/2 or 1.5 or 1.5. And I'm seeing a pattern here. Now if I plug in 1.5, that's 1 and 1/2 plus 2. That is 3 1/2, which is the same as 7 halves divided by 1.5 or 3 halves plus 1, which is 5 halves. This would be the same as multiplying by 2/5. Choose cancel, we get 7/5 or 1 2/5, which is 1 4/10, which is 1.4. Okay, there isn't a pattern. I thought this was starting to duplicate over here, but see what I mean is 1.5, 1.5, 1.66, 1.66. I thought this was going to be 1.2, but it's not. So it's not there's no pattern there anymore. All right, anyhow, carrying on, plugging in 2. 2 plus 2 is 4. 2 plus 1 is 3. 4 over 3 is 1 1/3, which is 1.3 repeating. Plugging in a 5, we get 7 over 6. Well, that equals 1 1/6, which is 6 going into 10, 1 time, remainder of 4. 6 times 6 is 36. And now you see that the 4 is going to repeat. So it's 1.6 repeating. Okay, number 10. 10 plugged into this will give me 12 over 10 plus 1, which is 11. Well, 11 elevenths is 1 1/11. Okay, so if I do long division with this 11, notice I'm not using my calculator for this. 11 does not go into 1. 11 does not go into 10. 11 will go into 100 9 times and give us 99 with a remainder of 1. Bring down the 0, it still doesn't go. Bring down another 0, and there's 100. 9 times 11 is 99. So you see what's going on here. We have a 1.09 repeating. So it's 1.09, where the 09 just keeps repeating. Plugging in 100, we get 102 over 101. Well, 101 over 101 is 1 with a remainder of 1 over 101. Okay. Sticking to my guns here, I'm not going to use a calculator. 101 going into 1.00. I'll just put a whole bunch of zeros here. Okay. 101 will not go into 100, so it's going to be 0. It won't go into 10. It won't go into 100. But 9 times 101 is 909, and I can subtract that now. And I go like this, and get a 1, and get a 9, and bring down a 0. Okay, did I do that right? 9 times 1 is, 9 times 101 is 909, leaving 91 from 1,000. Bring down a 0, we have 910. And 101 goes into 910 9 times. 9 times 101 is 909. And that's going to leave me a remainder of 1. And look what happens. We are back to 101 will not go into 1. It won't go into 10, but it will go into that. So it's going to be 0.0099 or 0099. So it's repeating. So it's 1.0099, where this all repeats. Okay, so what's it doing? 1.6, 1.5, 1.4, 1.3. Did I do something wrong there? I did. Number 5. Where's 5? Let's check 5 again. That's 7 over 6. That's right here. 1.16, not 1.6. Okay, I left a decimal out. Let me fix that. This is 1.0 or 1.16. Let's just do that. Let's fix that. So let's go over here. 1/6 is the same as this. And it will go in 1 time. There it is. 46 times 6 is 36. And there's my repeat. So it's 1.16 with the 6 repeating. So let's recap. 1.6, 1.5, 1.4, 1.3, 1.1, 1.0, 1.00. So these numbers are getting smaller and smaller and smaller, but this 1 is still staying consistent. So the decimal value is getting closer to 0. So we are getting closer to 1. Okay. Okay, page 3 brings us to the end of lesson 23. Here's the lesson summary. It says to compare two rational expressions, find equivalent rational expression with the same denominator. Then we can compare the numerators for values of the variable that do not cause the rational expression to change from positive to negative or vice versa. We may also use numerical and graphical analysis to help understand the relative size of expressions. So before I let you go, let's take a look at these two functions graphically, like it said. So if I plug into my calculator for y1, x plus 1 divided by x, and make sure you use parentheses, x plus 1 is my numerator, so that's got to be in parentheses, divided by x. And then on the other, I have parentheses, x plus 2, close parentheses, divided by parentheses, x plus 1. Okay, there's my reminder. Close parentheses and hit enter. Now, if I graph these, let's zoom 6 because I don't know where I was last time. So look what's happening here. X plus 1. Did I do something wrong? Yes. Let's go back. Y equals x plus 1 divided by x. So let's go down here and let's just look at the right side because it said do not go negative. All right. So I did this correctly, but let's change our window to x minimum of 0. And now let's hit graph. All right. So there's our first function and there's our second. So it's hard to see what's going on here. So now let's change my y maximum, or my x maximum. Let's not go out as far. Let's just go to 5 and see what happens. So we're just trying to find a good representation here for our window, and notice it never crosses the x-axis. So let's not have any negatives in our y-min. So let's have the y-minimum, the x-axis of 0, and hit graph one more time. And now we have a nice window. There is the first function, okay? And there's the second. So x plus 1 divided by x and x plus 2 divided by 1 look like they're both converging on the same value. They're getting closer and closer to 1, but they just never seem to get there. And that's what's going to happen with rational expressions or functions. Okay, so that is the end of lesson 23. Go do your problem set.